Good afternoon, everyone. I'm Tharindu Hettiarachchi. I'm currently a graduate student at Georgia State University, continuing my PhD in cosmic, global cosmic muon development research. And in this research, we are mainly concerned about deploying a network of low-cost cosmic detectors throughout the world and develop a network that can capable of predicting both terrestrial weather and cosmic and space weather. As I said, we are mainly concerned about two aspects of space weather and terrestrial weather. So, so if you take a look at the left side of this slide, you can see the magnetic field of the Earth, and we have created a simulation of the Earth magnetic field using 2005 magnetic field data. And using that data, we have been able to simulate a cosmic shower that can trigger more muon particles. So if we change the parameters around the Earth, like cloud density, the density of the atmosphere, and things like that, we can see changes in these simulations. That means cosmic showers can affect our weather and vice versa. Then effect the changes in the atmosphere can change the flux of muons. So that's one aspect we are trying to monitor, and the other aspect is when the magnetic field reacts with solar flares. When there's a large solar flare or any other solar activity, there's a magnetic field that carries from the solar event. So those magnetic fields actually reconnects with the Earth's magnetic field, creating a disturbance. So those disturbances also can be captured and studied in our research. So we have two aspects: space weather and terrestrial weather. So in terrestrial weather, there are things that are not actually discovered yet, like the source of cloud formation and what causes the lightnings to trigger, things like that. But there are speculations that those could be results of cosmic events. Like when there's, before going into further slides, I will briefly describe what actually are those cosmic rays. So there are two types of cosmic rays. Uh, those rays coming from the outer uh, galactic cosmic rays, and the other one is coming from our sun, solar cosmic rays. So those cosmic rays interact with our atmosphere and creates muons and other particles, and those cosmic rays are made of uh, high energy protons and high energy neutrons. So those reacts with our atmosphere nuclei like hydrogen and nitrogen nuclei, and they produce kaons and pions, and those decay into muons. So those muons actually can be detected at Earth's atmosphere. And there are other particles that can be detected, but the easiest one to capture is a muon because it has a charge similar to an electron, but much heavier. Uh, so to create a low cost cosmic detector, the muons is the best option simply because of it has a charge and can be easily detected throughout the ground level of the Earth. And another thing is these muons carry a lot of energy and they can be penetrated about 10 meters of water. So this can be detected even inside buildings, underground, even under the ocean. So that's why our cosmic ray detector is detecting muons rather than other particles like neutrons. Uh, for example, there's a neutron monitoring detector network similar to our research, but those detectors are very expensive. So that's why we switched to neons. So we can build this type of a low cost portable detector. And so our research team has multiple areas focused in different departments at Georgia State University. Uh, this is one aspect, global detector network. So this picture is when we deployed 2 detectors in Serbia. And like that, we have deployed more than 20 detectors around the world across 6 countries so far. And another aspect is in-flight measurements. That's a similar detector to this, but much smaller. This detector is actually is capable of taking on flights, and we have been able to take one in a flight to Sri Lanka, to Nigeria, Russia, China, and so on. So another aspect, the main goal of that is to capture the muon flux changes when we go across the globe on a flight, and also the increasing flux when we take off. And another a future target is to build a cube satellite. And actually, the in-flight measurements detector is a prototype of that cube satellite. Another aspect is balloon measurements. As you know, balloon measurements are a popular method taking weather data like pressure and wind and so on. So we are trying to get a we are trying to actually observe what would happen if we send a similar detector on a balloon measurement. And another thing is STEM outreach. So as you know, not all the countries has a science like interest. So as like in United States, we have to promote science uh, to school children to get them involved in science. So we are deploying detectors in high schools. Uh, this is Frederick Douglass High School in Atlanta, and we have also deployed another detector in Massachusetts. Likewise, those uh, high school detectors are placed on those high school to get them involved in science early on in their age, so they can communicate between other schools and collaborate with our network to analyze data. So they have been given permission to play with our detector, play with our data, so we can increase their curiosity in science. And let's move on to the next slide. So as I said, this is our ground-based portable detector, and this is what inside the cube satellite or the in-flight measurement detector. The main difference is the scintillator size. In the ground-based detector, we are using a 20 by 20 scintillator plate, and in the uh, portable CubeSat design, we are using 9 by 9 scintillators. So each detector has 3 scintillators. These scintillators are capable of producing photons when there's a charged particle going through them. So what we do is we capture the photon using a photomultiplier. We are using a silicon photomultiplier, and that silicon photomultiplier captures the number of photons, or the light pulses goes through the scintillator plates when there's a charged particle. So why we have 3 layers is an interesting question, because as you know, in electronics, there are multiple sources of noise. So if we just capture photons going through a single layer, and we would get numbers like this. This is counts per minute. So even though there's a 1400 uh, counts, only 144 muons has been going through that layer. That's because of background noises like thermal noise and shot noise and things like that. So what we have done is we have put three layers with a 13 centimeter gap between them to get the coincidence count. Like when there's a charged particle going through two layers, we count it as one. So as you know, the muon has a speed similar to very close to the speed of light. So if we get a pulse from the first layer and the second layer at the same time, we count it as one. So in each minute, we count all the pulses and we log them in our Raspberry Pi. So the first two layers, this first and the third layer, and the second and the third layer are recorded at each minute interval. And we also sometimes get dark counts by having a light blob scintillator. So this is not actually connected to anything, just wrapped in black plastic. So this is just recording noise. So I will explain the use of that in later slides. So if you join our net detector research, and this is what you would see when you use our data files. So approximately the whole thing costs around the cost of an iPhone. That's our main goal, to keep the cost down to an iPhone cost. So you might say like that's way too expensive, but actually when you think about particle detectors like neutron monitors around the world, like Ulu neutron monitors, they cost millions of dollars, but this costs only about $600. So the main brain of our detector is a Raspberry Pi, and we have our GSU build readout electronics and scintillator plates. The whole thing is assembled at Georgia State University. So, so if you take a look at our assembly line, we 3D print all the housing at Georgia State University, and this is the one we sent on hot air balloon measurement, and this actually went to Alaska on a flight. So, and this is where we assemble all our frames. And our readout electronics is actually being sent out to China for assembly because they take a lot of time. But Georgia State actually designs everything from scratch. So, so whoever joins our network are capable of designing future generations of our detectors. So, so when we assemble everything, we also place the the photo multiplier on PCBs like this. Our photo multiplier is 2 millimeter by 2 millimeter. This is what you would see inside the scintillator plate. So, so this is the picture of the scintillator. What's uh, inside these two plates? So inside that scintillator, we have cut out a groove that can fit a wavelength shifting photo fiber. So the goal of that is to capture all the photons that are being created at corners that are far away from the photomultiplier that is sitting about here. And also it allows the the photomultiplier to capture the photons that are in the wrong wavelengths, that are out of the wavelength bandwidth of the photomultiplier. And then we sorry, Then we cover the whole thing with black plastic to limit background light from coming into our photomultiplier. And this is our final design. And then we attach those into the three acrylic sheets you see here. And that's pretty much it when we are building a detector. So a very simple design. So once we build a detector, we test it for about 7 days. First, we keep a benchmark using two type of detectors. This one right here is a very stable detector that is exactly the same as the one we are building right now. And then there's another type of detector built from normal photomultiplier tubes. Uh, these photomultiplier tubes are very stable but very expensive. But that's why we are not using them, and very heavy. But since they are stable, we use them to compare with our newly built detectors. So once we build a detector, we keep it right next to a similar, very stable detector, and we compare with those two detectors to make sure our newly built detector is behaving exactly the same. So the plot you see is the flux percent change, and this is plotted using hourly counts. So as you can see, the patterns are almost the same, even though there are some noises. So I will explain a little bit about the electronics, what's going on in the Raspberry Pi. So this detector is designed by me, and so what we usually do is we grab the analog signal coming from the photomultiplier. So that comes from a UFL cable and goes directly into our circuit, and there's an amplifier. So as you can see, the analog signal goes through an amplification process, and then it's sent out to an FPGA where all the logic is happening. So all the coincidence counts and comparisons happen in the FPGA. So that FPGA creates a digital pulse whenever it detects a muon coming from two layers. So all the three combinations are sent out to the Raspberry Pi using interrupts. So then the Raspberry Pi captures those interrupts and saves them on a log file. And usually about every 2 hours, we send out the data to our GSU network, our servers at Georgia State University. And we are always in the development. We are always looking forward for future generations of power detectors. So as you can see at Colombo, we have two detectors. We have the first edition as well as this version 2 of our second edition. So this is the edition 2, version 2, and we also have edition 1. So the difference is that the amplification process happens at the SIPM, whereas the newer version, the amplification is done at the readout electronics. And so we have moved from 8 channels to a 4 channel design to get the cost down. And we are also capturing pressure and temperature in newer versions. So that's our evolution so far, and we will probably be including a magnetometer in our next design. And this is our map so far. We have deployed more than, right now it's more than 20 detectors across to deploy few detectors in South American region in the coming months, because we have been notified of the magnetic anomaly around this region. So if you take a look at a map made from magnetic data from the Earth's magnetic field, you would see a dropped magnetic field around South American region. And The reason we are interested in Sri Lanka is because we are surrounded by ocean so far, so that we can detect oceanic effects, and also we are very close to the equator. And another reason is we are interested in the gravitational anomaly around the southern part of Sri Lanka, where there's a very low gravity. And also, when there's a solar flare, since these detectors are right about the opposite side of the uh, Earth's equator, we can detect the changes in the magnetic field when there's a solar event, right? Like if you have seen a solar flare happening, the magnetic field would extend to protect the Earth. So we could, by having two detectors at the opposite side of the Earth, we can probably detect the changes in the magnetic field. And using that data, we have been able to detect solar flares about 2 hours ahead of NASA's data. So the aim is to deploy as much as possible and increase the detector network so that we can predict solar flares and Earth atmosphere changes before everyone else, so that we can have a global model of the Earth atmosphere as well as uh, solar events. So, so far, we are struggling with some aspects. Like in Nigeria, there's a major problem with power stability, and in countries like Australia, Singapore, they are very strict with their uh, policies of about data sharing. Like they don't allow us to send data to their servers. So countries like Sri Lanka are a very important place because we are very open to new research. So that's why you see three detector centers in Sri Lanka. Right now we have two detectors in Colombo, one detecting Wellasta University, another one in Ruhna University. And so these are some plots we took right after the very big solar event that happened around October. So before that, I will explain what these plots mean. The red line you see is the cosmic muon flux percentage. So in a typical day, you would see plus or minus 5% change. But when there's solar activity, these numbers go very low, like you see here. And when there's very big pressure changes, you would see a very uh, high numbers. That means the pressure you see from the blue line is and perfectly anti-correlated with muon fluxes. So that's why I said that the changes in atmosphere is very sensitive to our muon data. So this big drop in pressure is the Hurricane Helene. You might have heard from news, and again you would see a drop in flux in here. That's exactly what's zoomed in this section. So if you pay attention, you would see that when the pressure goes high, the flux percentage goes down. And likewise, we have been able to identify similar patterns with moon's position and wind direction and so many other parameters. So if we have enough data from all around the world, we can build a model about wind pressure, cloud density, and so on. So another thing we can observe from this plot is countries like Sri Lanka and Singapore uh, behave very strangely compared to others. That's because we are close to the equator. And because of that, we have what we call a higher rigidity. That means countries around the equator get only high energy muons because the magnetic field lines, um, uh, so the cosmic rays has to go through many magnetic field lines compared to like the higher altitude countries, like the latitude countries like America. So countries around the equator has a higher rigidity. That means we detect only high energy muons. So that's why you don't see auroras in Sri Lanka, the countries like Sri Lanka, uh, because we don't get much sensitivity because of the magnetic field lines around the equator. So if you focus on the second plot, uh, these are two major solar events. And whenever there's a solar event, we get a drop in count, like you see here. So that's because the magnetic fields get stronger when there's a solar event, and that causes a reduction in cosmic fluxes. So if we plot other parameters like KP indexes, and there are so many parameters from that we can get from NASA's satellites. So if we compare those data with our data, we can actually detect a solar event much before NASA can. So if we have a much broader network, we can possibly predict a solar event as early as like 7 hours. Compared to NASA, they can predict an solar event about 2 hours ahead. And this is a plot that we took from that in-flight measurement device. This is the flight we took our detector to Nigeria. So as you can see, there's like about 10 times more flux when we are on a flight. So we take off from Atlanta to Paris. You don't see much change there, but then you land. But after you take off from Paris and then you go down towards the equator, you'd see a drop in count. That's what I told you. Like you flying towards higher rigidity regions, so you are getting more shield from the Earth's magnetic field to cosmic rays. And and the one thing missing from the, like, if you zoom in like in to regions inside the airport, you would see higher counts, like because of the X-ray baggage checking points, things like that. Like we have seen, like when we zoom in particular sections, we have been able to see other flux changes. And this is the balloon measurement we did. So we have been able to replicate what NASA got back in 2015. So this was done last year, and you can see the exact copy we got. So this is where we get the highest count of muons, and the balloon pops and goes back down. And then we once this is where the balloon pops, and when it drops, it reaches the same altitude as this point, and then the parachute deploys and it drops. So that's not what we are interested in. We are interested in the changes in the fluxes, but we can confirm that our detector is working by comparing those regions to what NASA got. So in the coming months, we are trying to deploy as many uh, detectors as possible, and possibly in drones. And that's about it. So we are trying to deploy detectors in these regions as soon as possible. So if you go to these QRs, and we are publishing our data every hour. So every night we are updating our website with the latest data. So you see the flux percent changes. So this website is currently on the development stage, but once it's deployed, you can download and analyze our detectors data. And if you find something interesting, you can join our network and join our research. And thank you very much. So if you have any questions, please do it.